they will travel at different velocities because of their masses, there I said. They encounter this magnetic field where the force exerted upon them by the magnetic field is a function of their charge, and we assume they all have the same charge, right? 1 plus unit charge, and importantly their velocity, which is related to their mass, right? So they experience different curvatures. So this is analogous to the dispersion of light by some element like a prism or a grating. You've got a bunch of, say, what would the corresponding term? Not polychromatic light, but polymassive ions, ions of different mass. Right? They travel through this magnetic field. Their directions of travel are affected to different extents based on their masses, right? And so they are deflected to different extents. Imagine you have some sort of a device here with a small slit through which only a certain mass to charge ratio or range of mass to charge ratios for the ions might actually be admitted to pass. Or you could have a planar array detector to detect all those simultaneously. But anyway, the important thing is this: the ions all traveling essentially not collinear, but all traveling parallel to one another. The paths all parallel. The paths are now no longer parallel, they're divergent. And again, the extent to which those paths are altered, given by that relationship right there. The link is to the simulator that I'm going to have you guys playing around with on Monday in my absence. It's described either exactly the way I want you guys to work with this simulator as described in the lab procedure for this module, or I might let you know over the weekend. Oh, you didn't hear this, Ms. Mitchell. Over the weekend, you'll hear from me on the specifics of how I'd like for you guys to spend an hour or so on Monday to make up for the missed class time. But check this out here, guys. This is a pretty nifty simulator. You have your choice of ions over here, or rather, you have a choice of analyte species over on the right-hand side there. You will assume that they'll all be subjected to electron ionization, generating the monovalent cations up in the gas phase. And then, excuse me, and here's the ion source right here on the left. And then introduced to this magnetic field, you get to vary the strength of the magnetic field right here. Right? The strength is sort of suggested by the density of those little circles and dots. As far as the speed of the particle, that's also adjustable. Now, what parameter? There's a rhetorical question, or you could answer it right out of your mouth right now if you like. You get to adjust the velocity or speed of the particle. Now, how do you do that realistically with an actual physical mass spectrometer? There's a parameter that you can adjust that will alter the velocity of the particle, the ion that's being analyzed. So I'll check this out. We'll go back to the default settings. We'll pick the lightest and the heaviest. Here's the lightest of the species, the lead-206 isotope. And if you inject that thing, right, you fire basically directly upward, purely vertical. And the Lorentz force causes it to follow a curved trajectory, and then it strikes. And actually, this is intended to symbolize an array type detector. Got a little spot right there at about 60 centimeters where that ion struck the detector.
The curves are going to trickle upward, right, with the mass?
Say again?
The curves are going to trickle upward, like when you drop a rock in the water, how it trickles up. The circles are going to trickle up, varying mass, right?
Well, we certainly expect to see a different radius of curvature.
Yes.
Right? So, I mean, right now there's a semicircle that path is the simulator set up nice.